much as I need.
All right, perfect. Welcome, everybody. Thanks for being here. Morning number 2. Who's excited to hear the speeches today? We got some good ones. We got some good ones lined up for you. Just to follow up a couple of notes for Aaron, what Aaron said. The surveys are at your desks. If you would please fill those out. We do look at these and we do assemble the information and use those for putting our programs together for the following year. So if you would, please, there's places for you to add comments, but also to rate each of the speeches that you hear during the conference. And again, there'll be boxes out on our registration desk for you to hand those in at the close of the conference. Also, to follow along, if you all are interested at all, we are always looking for new members for the board, but even that, if you find a board member, thank them for all the work that they do to put the conferences together and bring you all together. So we really appreciate you all being here. Thanks. So I have the pleasure of announcing our next speaker. Dr. Theresa Crimmins is a director of the US National Phenology Network. She told us she wears 2 hats. Not only is she the director of the National Phenology Network, but she's also an associate professor at the University of Arizona School of Natural Resources. She's been published 80 peer-reviewed articles and book chapters. Her writing has appeared in Scientific American, The Hill, EOS, Nautilus, Popular Science, and more. She's appeared on NPR as well as PBS. She said she recently did a TED Talk, and we're really excited to have her here. She is going to be talking about her book. And welcome Theresa Crimmins, and she's going to be talking Predicting the Next Move. Thank you.
Thanks so much. Okay, can you guys hear me okay? Okay, good. I got the... All right, it's so great to be here. Thank you so much for being here. And I have to tell you, coming to these kinds of meetings are some of my favorite because I love overhearing everybody talking about the elms and the maples. And oh my gosh, it's so great to be up here with magnolias behind me. It makes me so happy. So I'm glad that this presentation is the first one in the morning. Hopefully you've all had plenty of coffee because the organizers asked me to do something that would be legitimate for your CEUs. And so when I present, I don't usually put a lot of graphs and math and stuff in my talks, but I did drift a little more in that direction this morning. Sorry if this is echoey. But I will try my best to explain everything thoroughly so that it doesn't totally overwhelm you. Okay, let's see. What do I need to point this at? Help, IT, help. How do I advance the slides? Is this on? Thank you. Okay, so we all wish we had a crystal ball, right? There's so many points in our life where it would be so great to be able to know the future. I always really appreciate if I have an umbrella, if it's gonna rain. It's really nice to know whether the store is going to have stuff I need in stock when I go. And one of my biggest challenges, honestly, it seems like these days, is knowing when the pharmacy is going to be open when I go to pick up my prescriptions. I wish I could just have that knowledge in advance. And when it comes to taking care of trees and other plants, there's a lot of opportunity to have advanced knowledge to really enhance what we're doing as well. When we plant, it's really helpful if we plant things not right before a freeze event, for example, or spreading herbicides or pesticides right before a rain event. It's really just helpful to have that kind of advanced knowledge. And that's definitely true when it comes to trying to control pest, insects, and other problematic pathogens. And so as Anne kindly stated when she introduced me, I lead an organization called the USA National Phenology Network, and I'm actually going to talk more about phenology and a lot of the other stuff that we do in my second talk later today. However, I will, just in case you're not sure what phenology is, right out of the gate, it is when stuff happens in plants and animals seasonally. When we see things like leaf out occur or when insects hatch from their eggs, and what are the environmental conditions associated with that. And so that intersects with our ability to be able to predict when those things are happening. And there's a lot of, again, opportunity and benefits that can come from better understanding when things are going to happen to optimize decision making and when we undertake different kinds of management or control activities. And as an example, pine needle scale, I actually don't know. Do we have that around here? Okay. What I understand, I'm a plant person, but I'm not a pest person. So if I say things wrong, somebody just shout out and correct me. What I understand is that pine needle scale is this scale insect that, again, you guys probably know better than I do. At least in cooler environments, overwinters, the eggs are protected under that white waxy scale. And then when they hatch in the spring, the little bitty crawlers zoom around for a few days, then they latch on. They are a sap-sucking insect, so they start sucking. And there's really only about a week or two before they start to develop that waxy scale. And once they have that waxy scale, they are pretty much impervious to pesticide. And so if you're trying to control for this insect, what I understand is that it's really important to understand when are those eggs hatching, because that's the start of your window of opportunity. And it's not the same calendar day every year when that happens. It's really actually a function of what the recent conditions have been like that prompt those little guys to come out of their eggs. So to kind of jump to the end, this is the kind of product that we offer through the USA National Phenology Network. We produce maps, and in collaboration with other organizations as well, we produce maps that indicate when we think those kinds of events, like when the pine needle scale crawlers are going to be out, so that you can use that to help plan when you need to be taking those kinds of actions. And so in this map here, what we're showing is that this was captured June 5th last year. I didn't grab this year's map because there's not a lot happening just yet. But in the middle, at the beginning of June, every area that's shaded yellow is where we think that the crawlers are actually emerging. And so if your location on June 5th fell into that, was shaded yellow, this is your time to start taking action. If your location fell into one of the green shades or blue shades, you can look at that, the legend down in the lower right there. You are actually getting close. And what we try to do is anticipate and give a little bit of time warning there, like you're a week away or you're about 2 weeks away, given what the environmental conditions have been so far. And if you're in the orange, you missed it. If you're in the gray, you really missed it. And you need to just worry about it for the next year. So hopefully this kind of map, and these update nightly, and so you can either consult it, on a nightly basis to see where things are at relative to your position, or you can kind of even look south or down slope, because that's kind of your indicator of what's coming. But how do we get there? What is behind this map? How do we make these kinds of predictions? And are they any good? Can we trust them? Okay, so backing up, when I mentioned phenology, again, there's really kind of two pieces to what the definition of phenology is. It's when these different seasonal events in plants and animals are occurring. So like, when do the terminal buds open, or when do the flower buds start to crack open? We start to see the petals emerge. And again, with insects too, when do we see adults emerge, or when do we see things going into, what's the right word for insects overwintering? When do they overwinter? When do they initiate overwintering? And it's actually a function of environmental conditions. Things like day length, temperature, rainfall. And it depends on what species, it depends on the location, it depends on which life cycle event we're talking about. All of those things play a role in defining how well we can predict when something is going to happen. And how do we figure that out? Well, there's a couple of different ways. Lab-based research is one of the ways. And basically, people either put plants in growth chambers or insects in growth chambers, very controlled environments where you can know exactly how much daylight you have, the hours of sunlight, equivalent of sunlight, and then you can control the temperatures very closely. And if you do this, that's a way to figure out, like, what are the exact conditions that seem to be necessary to initiate, say, leaf out or emergence or molt. But that's expensive. That's very expensive. Growth chambers are tens of thousands, if not hundreds of thousands of dollars, and not very many people have access to this. So there are other ways too. Field-based methods are actually another commonly used approach. And what that involves is going out and just making repeated observations on your organisms of interest. And in this case, this person is looking at both flowers. Oh shoot, what's this one? I haven't had enough coffee this morning. Something foam, sea foam, something, that plant, that lovely plant that attracts all the butterflies, and they see butterflies on there too. And so they're saying, on this particular day, I know that this plant is in flower, and these butterflies are present as adults. And that's going to be important information, because if you make those kinds of observations periodically over the course of the season, and then ideally over several years, you can then start to actually construct a picture of when did those events occur, and what were the conditions that were associated with it or that preceded it. And so in this slide I have that person, that observer, looking on several different years and paying attention to the temperature. I'm going to focus heavily on temperature here because especially for springtime events, but honestly throughout much of the growing season, temperature is the biggest driver. It gets a little dicey to say that in water limited systems like we're in right now and actually where I'm at in Tucson. But for the bulk of the country, most events really are largely controlled by temperature, either warmth in the spring and then the summer, or warmth followed by chill in the winter. And then sometimes also the amount of day length plays a role, and sometimes also moisture plays a role. And again, I feel out of turn saying that here because yes, actually moisture plays a really important role in the desert Southwest. But I'm going to stick with the temperature story because it's an easier one to tell. So in this example, this person has gone out and observed when they're seeing that particular species in flower, or that butterfly as an adult, and they're able to know, okay, how warm has it been? How warm has it been the last, like, say, month? What's the average temperature? And then if you have those observations, you can plot them. And so in this plot, I do. Oh, excellent, okay. But I can't shine on both, sorry guys. Okay, the x-axis is, what I have here is average seasonal temperature. And so this is a relatively commonly used environmental variable. Seasonal temperature is usually a 3-month average. So winter is December, January, February. Spring is often March, April, May, although you can summarize that however you want. But say we're looking at an average seasonal temperature, and then we have those, that's what's plotted on the x-axis, and then the y-axis is the day of year, or sometimes abbreviated DOY, I might have that on some of my slides, that event occurred. So if we go back to this slide, basically what we're saying is each one of these years becomes one of these points on this plot. And so I should have probably given them labels, but if we said this was year one happened to be a very cool year compared to the others, and the event actually occurred much later in that year than in any of the others. And then in year 2, we had completely opposite situation. It was a very warm year, very warm season, and that event occurred much, much earlier than in those other years. And then we have a few more years where it was kind of a mixed bag. And we can plot a line through these. Again, this is like the most simplistic example. And then we can even figure out, does that line tell us anything? I didn't put a significance on here, but actually if you're really trying to establish what that threshold is, as a best practice to understand, is this trend that we're fitting or this relationship that we're fitting actually statistically meaningful? The important thing here is that what we can do is figure out if there's a relationship there, can we do something with it? And in this case, the answer is yes. So if you remember your math from middle school or high school, and I will just admit, yesterday I was puzzling over this very simple linear equation, and I had to ask my 17-year-old, what's the slope of the line again? So just so you know, like I'm right there with you. It's 1.1. This is the good old y equals mx plus b linear relationship between two variables. The slope is, what's that rise over run? What's the slope of this line? Meaning, for every degree difference in average seasonal temperature, how many days earlier does that event occur? And the slope here is minus 1.1. And so this is a made up example. It's totally made up, but I needed it to work, so that's why I made it up. Because in the real world, data don't always behave as well as they should. Basically, in this made up example, if average seasonal temperature is a degree warmer, then this event that we're looking at, either that flowering or that emergence of the adult butterfly, occurs about a little over 1 day sooner. So that's just kind of an example of how we put this information together to be able to then make predictions, because if we understand what are the conditions associated with the event, then we can begin to put them into a predictive way if we are watching what the weather is doing in real time. Okay. That's a very simplistic way of doing things, though. Again, average seasonal temperature is a little coarse. It's good for building simple relationships, but when it comes down to making real-world decisions and in an immediate real-time context, it's not great, because to come up with an average seasonal temperature, you need for the whole season to have occurred, and then you can figure out what that average seasonal temperature was. So that's not super helpful if you're trying to figure out something in real time. So folks working in this space have come up with other ways of doing this, and you might have heard something called growing degree days, but this is actually a commonly used approach in pest management and agriculture and other spaces where folks are trying to predict, again, when things are going to happen, especially if we understand and assume that temperature is the primary variable driving that thing from happening. So in this plot here, what I've got is just a nice little curve that depicts what is the daily temperature doing at any given location. We can think of this right here, right now. Over a 24-hour period, basically, this is a little idealized, but the temperature is lowest in the early wee hours of the day. And then as the sun comes up, it gradually warms, it peaks early afternoon, and then drops back down. This is what organisms are paying attention to. And they're actually paying attention to this day after day after day. So we can kind of try then to characterize what those temperature conditions have been like in a given day, and then again that sequential day after day after day bit, because that is what actually organisms are paying attention to, as we think, as humans. This is all like a human construct for what they're actually doing. Okay, so this is kind of taking that idealized plot and turning it into how we actually calculate what the warmth has been like that the organisms are getting exposed to that we can use in a predictive sense. So this is basically the same kind of curve. What we're looking at here, again, is on the x-axis, this is just time. So 1 hump equals 1 day. And on the y-axis, we've got that daily temperature. So when we're working with growing degree days or thermal time or thermal units, it's basically the concept is an organism will respond by opening its buds or starting to leaf out or starting to go through those different molt stages after it's been exposed to a particular amount of warmth. So it's not just how warm is it on any given day, but actually the organisms are, again, human construct, but the way we can think about it is they're integrating over a whole period. And if we're thinking again of seasonal environments where they go into diapause or some sort of rest state in the winter, then they need to be exposed to a particular amount of warmth before they start getting active. But we know our weather is ping-ponging all over the place, and it's getting to be where it ping-pongs even more. We might have one really warm day very early in the year, or maybe a run of a couple of warm days, and then it gets really cold again. And then it might start to warm up again, and then it slows back down. And it's tricky to know how the organisms are going to respond to that. But this growing degree day accumulation, meaning kind of tracking how much of that warmth these organisms have been exposed to over some period of time, is actually some way that seems to work pretty well in a lot of cases. And so, but the point I want to make here is that there is a lower, what we call a lower threshold or a base temperature below which they just stay inactive. And so what we're looking for is really daily temperatures to be above some sort of base temperature, and that is what starts to get them going in the spring. And then there's actually oftentimes an upper threshold that's identified too, because once it gets too hot, organisms can slow down, and that can negatively impact them too. Although that's usually less of a situation in the spring. Okay, so if we take that concept and then we start to look at it day after day, this is kind of what it looks like. So again, the red wiggly line is what the temperature at a location is doing over, what do we got, 5 days there. And we've got our base, our lower threshold or our base temperature. We have what the temperature is doing day to day. And then it's this gray shaded area that says DD that is the amount of warmth that we care about, because that is what we believe is actually meaningful for the organism. And so it's the part of the area under the curve that falls above that base temperature. Because anything below the base temperature, again, it doesn't count because it's just doesn't impact the organism. And so there's a lot of different ways to try to calculate what this amount of warmth is and be able to keep track of how it's accumulating. Of course, if you're mathy, you could look at that and say, oh, calculus could be invoked here. Yes, it could. There's also various methods where people try to come up with a triangle that matches it pretty well, or even using sine waves. But what in reality works pretty well is just average daily temperature. If you just take the min and the max here, add them together and divide by 2, you get your average daily temperature. And basically what you do is compare what the average daily temperature is to that base temperature. However many units are above that base temperature is how many thermal units you accumulated in that day. And so I have kind of a made-up example here again, where say on this particular day at this location, we had actually, I think I did this okay. The temperature, the max temperature was about 70 degrees on this day. Our base temperature we were working with was 50, so the organism didn't respond if the average daily temperature was below 50. And so we figure out how many thermal units were accumulated in that day. I probably didn't do a great job, I just said 30. And if we were starting to accumulate on this day, we got 30 thermal units that day, and so our running total is 30. And then on the next day, it was a warmer day, so we actually accumulated, say, 45 when we do the math. We take the average daily temperature, compare it to that base temperature, and we were 45 thermal units above, so we accumulated 45 on that day. And then when we add that 45 to yesterday's 30, we now have a running accumulation, or accumulated growing degree days of 75 units. And we keep going. Say the next day was a little cooler, we only accumulated 32 units on that day. We add that to the previous day's running total. We're now up to 107 units. We keep going. The next day was another warm day. We accumulated 43 thermal units on that day. We add that to the previous day's running total, of 107. We get to 150. And then the final day here, 31 more. So now we're up to 181. And what I'm trying to show is that you're basically accumulating. You're figuring out how much warmth, meaningful warmth, did your location experience in a given day, and then you keep a running total going. And you can then plot that running total. So what I'm doing here is taking this bottom line and plotting it day over day. And so now what we've got on the x-axis is the date, starting on, should be January 1st. And then on the y is that accumulated growing degree day units. And this is generally what these curves tend to look like, where there's really, okay, I should back up. Usually accumulations are started on January 1st. And that's basically because it's arbitrary. Plants and animals do not care about the Gregorian calendar that we use. But it's basically the middle of winter. And so again, in most locations, it doesn't matter if you start accumulating on December 1st or January 1st or February 1st, because there's not going to be any meaningful warmth being accumulated in those early months. The daily average temperature is going to be below your base temperature, so just start accumulating on January 1st. It's easy, it's an easy calculation. There are some locations, sometimes people use actually like March 1st in northern regions, because again, you can have those wacky weather events that occur very early. It's a really warm day in early February in upper Minnesota. That does not have any meaning for organisms, and so people just discount it and say, we aren't going to start accumulating until March 1st. But most of the time, people just go with January 1st. So that's why you see that there. And in this location, this was actually the town I grew up in Michigan, Howell, Michigan. Last year, 2024 actually, very early in the year, all of January, we didn't accumulate any growing degree day units because it was cold. It's just cold in Michigan in January. But then later February, March, we start to pick up a few. And then it started to get a lot warmer in basically May. And then the slope of that line starts really picking up. And you can see that the number of units that you're picking up grows rapidly. And this is really when a lot of stuff is occurring. That's when you're starting to hit various milestones and trees are leafing out and insects are emerging and lots of stuff is happening. What's interesting though is that it's different every year. And that is again because the weather is different every year. This is plucked from Paso Robles, California, and I grabbed it just because it's a nice plot showing that growing degree day accumulation curve plotted for several years over the year. So again, they started accumulating on April 1st. So looking at April 1st through the end of the year, each colored line is a different year. And so some years it was warmer, and that's where you get those higher accumulations. Some years it was cooler, and so you just see that as lower accumulations by the end of the year, and others kind of bob around. Okay, so this is how we can characterize what daily temperature is looking like over the period that matters to organisms. Great, now what? What do we do with that? All right, I'm gonna pivot really quickly because one of the things that we offer, again, the USA National Phenology Network, is we are calculating those growing degree day accumulations for you all across the whole country on a daily basis. And I plucked this map from last year. This is June 16th because the maps are a little less interesting right now because much of the country isn't doing anything. But what I'm showing here is that the amount of growing degree day units that have accumulated by June 16th varies a whole lot across the country. And this is probably no surprise at all. We have far more units that have been accumulated in the southern states where it's warmer than by June 16th than in the northern states. But I'm trying to set this up because basically what we're doing is we can calculate the accumulation at any given location, and we can also look at it across space and see how it varies across space. We'll come back to this. We'll come back to this map if it's not making sense just yet. Okay, so coming back to an accumulation at a single location, if we, again, are kind of going back to, all right, if we want to figure out what are the conditions that prompt an organism to leaf out or flower or put on its leaves, and we don't have access to growth chambers and we're doing it on our own, this is effectively what we're looking for. We're trying to figure out what is the amount, that magic number, where the green line is intersecting here. The green line is, when does that thing happen? We're trying to figure out what is that green line. We're trying to figure out what is the amount of heat that needs to be accumulated before we go from the event not happening to the event happening. So how do we solve for green line? Basically, it's this. We go back to looking outside at our organisms, figuring out what they're doing, and then actually looking back at something like the tool that my network has, which is telling you how many heat units have been accumulated at your location by the date that you saw the thing happening, and then looking at that. And so, oh shoot, one of those is missing. I had an example here where it was about 298 in the first, let's see, yes, year one. We first saw the flowers happening, and when we looked at the plot, we figured out that there had been about 295 growing degree units that had been accumulated when we saw that happen. In year two, it was 298, so it was really similar. In year three, when we first saw the flowers, it was more like 320 growing degree day units had been accumulated. And then in year four, we looked again, and it was around 300. So we did some math, and we said, okay, if we average those four numbers, we basically can say that event happens around 300 growing degree days. And I don't know why I put a pine needle scale there because that's not the example I was talking through. But basically, it's a matter of simply looking to see when did your event happen and what were the conditions that preceded it. And so coming back to this map, that's basically what is behind these. We are taking those daily growing degree day accumulations, and then this is a situation where someone else has done this work for me and has said, we know that pine needle scale crawlers emerge after about 300 growing degree day units have been accumulated. And so then what we do is we just take those maps where we're figuring out how many growing degree day units have been accumulated across the whole country, and we're just reshading it. We're basically saying, okay, well then where are the locations where we have reached 300? And those are the yellow, painted yellow. Where are the locations that haven't yet reached 300, but we're getting close? And then we did a little bit more math, and we said, you know, we estimate that if you fall within 172 and 231 today, then you're probably about between 1 and 2 weeks out. It was again like a little bit of back calculation. These are not perfect because again, it's the weather. It's a function of the weather. But basically, that's what we're looking at here: is do we think we've had enough warmth that has been that our location has been exposed to that would prompt us to be ready to see this event occur, or not quite yet? Okay, but is it that simple? Sometimes models really are just basically heat accumulation, the growing degree days. In reality, that again is probably an oversimplification for a lot of organisms. It does work. It does work in a lot of cases, really, and in a lot of locations. And so it's a very commonly adopted approach. Sometimes we do have to consider other variables, though, too. There are definitely, and I imagine you guys know, there are plenty of plants in particular that won't pay any attention to any warmth, no matter how much warmth they're getting exposed to in the spring, unless they've had enough chill. And then all bets are off and the models aren't gonna work. Or sometimes they are day length limited. Plants and I think some insects too, won't respond to very early season warmth if the days don't have enough hours of sunlight yet, because they're like, no, it's not time. I know this is a protective mechanism to keep me from, you know, putting my tender tissues out too early and then get zapped by frost. I'm gonna wait till there's enough daylight hours, and then I'll start paying attention to warmth, and then I'll start responding. And so there are increasingly more complicated models that try to factor those kinds of conditions in and make the predictions. And my team has been working closely with folks out of the Oregon IPM Center and some other folks, Forest Service, USDA, to figure out, you know, what are the models that best work for these various organisms. And these are right now the different species and events that we have those predictive, what we call Pheno Forecast maps available, and that are running nightly, and that you can consult to see, hopefully, when these things are likely to occur, and hopefully help you in your planning and management for them. I will warn, some of them, if you go to our website right now, aren't quite functional yet. We have a lot of back-end server stuff to deal with, and we knew that some particular pests aren't gonna be coming online for several more weeks or even months, and so if you go check them out, not all of them are up yet, but they will be. One of the enhancements that I want to mention is that working with our partners at Oregon, the Oregon IPM Center, is that they have added to the models not just when the stuff is going to occur, but also where is it not going to occur. None of our maps account for where the species is. We really expect that it's more like, well, it could be here. It's up to you to know if it is there and if you need a tree for it. If it is there, this is what stage we think it's going to be in. But the Oregon folks have taken it a little bit further and said, well, there's definitely areas where things can't be found. This is the map for spotted lanternfly, which is rapidly expanding, as you, I'm sure, know. And so it could be found. It is not yet found in many of these states. Could be found there if it was on this particular day was, let's see, this map was May 8th of last year. As of May 8th last year, if you were in Kansas City and you happen to encounter it, it's not going to be doing anything yet. However, the Rockies for sure, and Yuma, Arizona, we're not going to see it there. It's just like completely inappropriate conditions altogether for them. The other enhancement we made with working with the Oregon folks is that you'll notice that the legend is different here. These are long lead forecasts, and we translate it into, do you think it's going to be in the next week, the next month, 3 months out, which is a really cool enhancement. So this kind of stuff hopefully can be really relevant for things like knowing when to put out traps. If you can anticipate when and look at the maps and see when are the adults for a particular insect you want to control likely to come out, you can get your traps out, and hopefully not so early that they're going to get, you know, beat up or taken down or something. You kind of hit that window, that sweet spot. Also help you, of course, apply the insecticide when things are most effective, like with the pine needle scale. And then also, if you're in the business of releasing the parasitoids, those beneficials, that can, you definitely want to time that well as well. This is an example where one of our collaborators at Oregon State actually used the map for early, some surveillance work, some early detection. And I believe the person that collected all these dots was with he was with the state. I can't remember. I think it was Washington State. And what he found was that the trapping sites, they could figure out when the adults of emerald ash borer were coming out, and the maps actually did a really pretty good job at predicting when the events were occurring there. So that was encouraging. Okay, one feature that I do want to mention is that you don't have to always go to the website to check out the maps if you don't want to. That's a lot of mental burden to remember to go check it every day or every week or whatever. So we try to make it a little bit easier for you. You can sign up to receive notifications through email. And so the URL for doing that is on the bottom of the slide there. But you can sign up and say, hey, I want to be notified for these 6 or these 7 events. To let me know. And it's zip code based, so it's relatively tuned for your location. However, elevation might throw you a little. So it's hopefully a reminder to get information and then go maybe check it out a little further on the website. Okay, but what if we don't have the right map? What if I showed you that list of 15 or 20 different species that we make forecasts for? I'm sure you manage for many more than that, and we don't have all those maps live. Well, we do have those underlying growing degree day accumulation maps, and you can check those out, and you can do the manual labor of figuring out what the growing degree day thresholds are on your own and checking that. Or there are actually a lot of lists that have been published that people have tried to do the math and the work on their own and figure out what are the growing degree day thresholds for different events occurring. And so if you Google that, we're trying to compile that on our website. But some of those resources are available, and you can basically kind of do the longhand version of, I know that the thing that I care about is going to occur at 500 growing degree days. Let me just go look at the maps and see where my location is. Are we getting close to 500 or not? And we have what we call these pretty maps on our website that are, formatted nicely with logos and that kind of thing that you can just go look at. But then we also have, for slightly more advanced users, something called our visualization tool, where you can go in and actually pan and zoom in the map and then even drop a pin on it and get the exact value for the growing degree day accumulations in your pixel. These are based on Prism, if you're familiar with that, daily average temperature values. And so again, we're just doing that math in the background of figuring out how many growing degree days have accumulated in every single one of the pixels all across the whole country. And so you can use that to figure out where you are at relative to the threshold, that green line, that when is that thing going to happen? Are we getting close or not? And then one more thing that I will mention, because this is even more shortcutty, but there's pros and cons to shortcuts. If we don't have a map at all, but you just want to get a sense of, is stuff happening earlier or later than average at my location this year? We do this, we offer a couple of indices of spring. I know an index is not always the most obvious, the clearest concept. An index is basically sometimes unitless, but it's a composite measure of taking complicated information and trying to distill it down to something that just kind of gives you an indication of where are we at. Are we doing good? Are we doing bad? We're doing ahead, late. And so some of the indices that I thought might be helpful to just kind of help you remember, like, oh yeah, that's what that is. Body mass index is one, but I don't really want to talk about that. Consumer price index is another one that we hear about in the news a lot. And it's basically economists look at all these different factors, the costs of medical care and transportation and education and foods and goods and all these things, housing, and then we try to see like how strong is our buying power and how is that varying over time. And so it's not tied to any one of those things, it's all of those things kind of combined, and then it's like we basically can say, is it better or worse? Is it good or bad? Is it going up or down? The S&P index for stocks is another one. There are so many stocks that we could track, and largely we don't track individual stocks. We have this index, this kind of composite measure of a whole bunch of what we think are indicator stocks, and then we track that, and it tells us, is the stock market doing well or not? And so the stock market could be doing well, even though your individual stock that you care about is not doing well. But that's how that works. It's kind of this, like a bellwether, they say. So we have a couple of indices of spring, and that's the intent there is to tell you, is spring coming earlier or later? And I didn't update my slide. We have 3 indices. I have 2 listed here, and I apologize for that because the third one is just coming online this spring. But it's basically a measure of what the heat accumulation has been like and whether, when biological activity is going to occur. And so it's a kind of, these indices are basically fancy pants growing degree day accumulations. We are looking at average accumulated temperature and then also this other magic additional ingredient called synoptic capstone events, which basically mean when you have multiple days that are warm in a sequence, those kinds of events, like a real warm spell coming through, that's what actually really matters for plants and animals. Growing degree days, the way we calculated, the way I explained it before, it's helpful. It's helpful, it does a decent job. But when we really get down to what matters to plants and animals, those kind of big warm events really play kind of an outsized role. And so these indices account for that. And I will not talk you through the math because I can't. But again, tried to plot out. You can look at heat accumulation again over time, over the year, starting in the spring. And then there is, again, a magic green line. You know, when does that thing occur? And this is how it works, is we're calculating in the background how much warmth is being accumulated plus those synaptic events. And eventually, at a single location, you cross that green line, and that's the day that's the day that our spring leaf index was reached. And the leaf index effectively is a measure of, I feel like it's an indicator of when have we reached to conditions that the very earliest stuff that happens in the spring is just starting to get going. So it's when we start to just see those little buds open on early season shrubs and stuff coming out through the snow, if we are in a snow-covered area, maybe some of those very early insects. But that's what I really wish we could rename them, but that's what the leaf index is. We then have another index. We keep tracking the warmth that's being accumulated at a location. And after usually about 4 weeks after the leaf index is reached, we hit another threshold, another just kind of like line that we drew in the sand. We call that the bloom index. It is indicative of when shrubs tend to flower, early season shrubs like lilacs and honeysuckles. It's also pretty closely tied to leaf out and overstory trees. And so it's kind of an event that it's a threshold or a checkpoint that's a little bit later in spring. And then we just this year, are adding what we're calling our late bloom index, which is one more checkpoint that we feel captures kind of that tail end of spring. So again, if you think about spring, it's this whole continuum of events. We have maples that leaf out and flower earliest, and then you keep going and you get to your oaks, and then you get to your birches are early, other stuff is late. Who's the latest? Who's the latest to start stuff? And it's black cherry flowering and snowberry and a few other real late season things. The late bloom index basically captures those things and is, again, we're saying like these kind of bracket the spring season. And so we offer maps that show when are these different indices reached. And I know that legend is impossible to read, I'm sorry. That's the day of year. So if it's bright orange, it's the index was reached very early in the year. And then if it's green, you're much later. And so this gives you kind of an overall sense of, yes, there is a latitudinal effect to when things begin. And you can see too, they're both on the same legend. So the leaf index comes first, the bloom index comes a little bit later. But that's not that helpful, honestly. What we really want to know is it earlier or later than average? That's where the power of the index really comes in. And so you might have seen these maps before, because they do make it into the news pretty frequently about this time of year. Is spring earlier or later? And basically it's, if the location is shaded red, then yes, those conditions associated with the start of spring were reached early this is last year's map. And if it was blue, then they were reached later. And so last year feels like forever ago, I can barely remember it, but the very beginning of spring was slow. It was cold. It was just slow to get going. And so we didn't have any interesting stuff going on. This is always the part of the country that hits the leaf index or those conditions associated with the start of biological activity first in the spring. And we were late. We were weeks late in most of Florida, southern Texas, all those Gulf Coast states. Then we did have some warmth. We did have a warm something come through. I'm not a weather person. And we actually kicked things forward, and some locations actually hit spring, the start of spring earlier than average, and those locations are shaded red. But then we had a huge cold thing come through, and I think there were ice storms in Texas and stuff, and that resulted in a lot of locations further to the north taking a lot longer to accumulate sufficient warmth to be able to hit that index, and so they hit that late again. And then it got very warm, which is usually the story anymore, and much of the rest of the country hit the beginning of spring earlier than it usually is. And when I'm saying earlier or later than average, we take the current year and compare it to the previous 3 decades. So in this case, 1990 to 2020. That's just a standard climatological practice. And so last year was a mixed bag. There are other years that we've had in recent decades where this whole part of the country is the brightest red color. Those are usually the years where the New York Times and Washington Post want to talk to us like crazy and tell us, oh my gosh, what's happening, and is it bad, is it gonna be bad? Okay, so this is the 3 indices together, the anomaly maps, or the earlier or later than average, for all 3 indices together for last year. So this is interesting, I think. The leaf index, again, the one on the left, that's the one I just showed. That's, again, the very beginning of spring. And we see that story of like, it was early, it was late, it was early, it was late, depending on where you're at. By the time we got a little further into the season and hit the bloom index, much of the country actually hit it earlier than average. And that is because of those big, large-scale warm events that were coming through in, I think it was like April and May. And then, this is really wacky, my whole team had to puzzle over this. We had to make sure we didn't do something wrong. We hit the late bloom index earlier than average pretty much everywhere in the whole country last year. And again, that was because it just got warm, and it got warm over the whole country once we were later into the year, and that was more like May, June. So we are running these live right now. Oops, actually I'll skip ahead and then I'll go back. This is what the map for the leaf index this year looks like so far. It's really hard to see. There is a big white and blue blob here where things were late. We did have some early season warmth down in the Gulf Coast states that forced things to, say, yep, we're getting started. But then, as you know, it's been insanely cold and snowy, and all my relatives have been complaining a lot about how bad it's been and how they've had to get dump trucks to move the snow out of the cities and stuff in most of here. So we're not seeing anything going on there yet, but we still could. And the truth is, if it warms up and it sustains being warm, even after that crazy amount of winter cold that we've had, we could still hit stuff early. We could still see an early start to spring in all of the country. And we actually do have a long lead forecast that kind of runs in the background, and that does predict, it is predicting a lot of red for much of the country. So I'll go back to this really quickly, because I know that people oftentimes do struggle to make sense of the banding on the maps. I worked with some folks with climate.gov last year to try to do this little explainer piece, and I'm sorry that the URL is so long on here, but I can share this through other ways if you're interested. But it's a really nice, just short, public-friendly article that describes not only what's going on and why we see that kind of weird, like back forth, early, late, but also when you compare. This was last year, so we only had the 2 indices, the leaf and the bloom. But how can you can have a story where one thing is reached early and one thing is reached late, or vice versa. And so this is a story where we snagged it from Minnesota, where in Minnesota the first leaves were reached late. The leaf index was late, but then the bloom index came early. And what they plotted was that's the temperature anomaly for that location, and it was because it got just really warm between when those 2 events occurred. So this is a kind of a nice explainer that just kind of digs into it a little bit further if you're interested. Okay, and then the last thing I want to mention, I brought 2 handouts, and they are here somewhere. I only brought 200 copies of each. Oh, you guys have them. Oh, great. Okay, excellent. But they are available on our website, and I can send them to you directly if you want. But they do describe both sets of products that I just walked through, the Pheno Forecast on the left. That one, I think, is not quite up to speed, meaning that we have a few additional species and events that forecasts are available for that aren't listed on there. So you can check the website for the most comprehensive list. And then the other is about the growing degree day and spring index maps that are kind of those more shortcut or maybe long cut resources that are available for you too. And I have to give the plug. If you're interested in this, or I'll be talking more broadly about phenology this afternoon, I'm happy to talk to you more about it. And if you want to read about it, I do talk about the stuff that I just described in this presentation in my book that I have available for you for purchase today, if you're interested. Okay, thank you. I'm happy to take questions, and hopefully I didn't run over.
Any questions? Raise your hand and we'll get a mic to you. Coming.
Oh, hey.
So I apologize if I missed this. You're covering a lot of information. I guess the question is, how is your models affected long-term with sort of climate instability? For example, on your chart, it looked like you had our leaf out in our spring in our area in Silver City set to sort of an average, but we're seeing bees and blooms as early as like the third week of January where we are.
Do you mind? Thank you. That's a great question. Do you mind putting the slides back up? Can I go back? Oh, sweet. Okay. Thank you. I see something different on the TV down here. Do you mean this one here or? Yeah. There, I don't see anything showing up for Silver City yet.
We're observing.
Yeah, okay. I see what you're saying. Okay. It's a very good question. All right, so one thing I'm noticing is I updated this slide last night, but it seems like it didn't sync. There actually is more stuff that got colored in as of yesterday, and I was surprised because I snagged this map. This one shows February 8th, which would have been Sunday, right? And I updated it last night, and I was like, whoa, because a big blob popped there. And unfortunately, this isn't reflecting that. So yeah, we should look. You can pull it up on our website. Actually, you can go at usanpn.org, and there it is. There's a link right on the homepage, and if you click on that, you can go in and we can interrogate it. But yes, but honestly, thank you for saying that. They are indices, so they're not perfect, and there's a couple of things that I think could be at play there. One is that one is that these indices honestly do perform better in locations where heat accumulation is the most important factor. And I feel like a little bit like it starts to fall apart to some extent in locations where you don't have as concrete of a winter. And even so in Tucson, where I'm at, I'm always a little like, I feel like I'm on thin ice referring to these maps and using it as the most important thing to interpret. And so I feel like that's probably what's going on there, mostly. And then the other thing is that the bees that you're seeing and the things that you're seeing may just have different requirements than what this index is reflecting. And so again, this is like our best guess. This is kind of like the rough estimate of is it earlier or not. But now I really want to go check the map and see what it says for Silver City and see how well it does. So thanks for pointing that out. Yeah. Yeah. Come over here.
For somebody who has an interest in alpine plant phenology and has to factor in other variables such as the timing of snowpack melt,
Yeah.
I'm wondering if you have or if you know of any good resources for finding long-term data
On
snowpack
snowmelt, the date of snowmelt, or of when the organisms are responding?
Snowmelt.
I will have to look that up for you and follow up. Can you come speak to me? I'll get your contact info, because yeah, I think there is good resources, but I don't know off the top of my head.
Okay, that would be great.
Thank you.
More questions?
What's that?
Everyone, please silence your cell phones.
Any more questions?
One over there. Yeah, there's a National Snow and Ice Data Center out of Colorado. That's what's coming to mind to me, but I feel like there's probably NOAA products and like you're hinting at, and But I also don't know what the availability is. Things are a little dicey these days, so yeah, I do know people that know. That's what I'm thinking of, is I'll ask the people that know. Yes?
Yes, could you share your thoughts on how this relates to irrigation advice, especially with a mind towards water use efficiency?
Yeah. So in the situations where available moisture plays an important role in cueing when things will occur, that does kind of muddle it up, honestly. Again, temperature-based models only assume that available moisture isn't a limiting variable. And so that's, again, where I was saying growing degree day models and even these spring indices work pretty well in locations where, you can just assume that you have enough rainfall. Yes, out here where we do need to make sure that we have sufficient moisture in order for plants or animals to be able to take advantage of that incoming solar radiation and temperature is a complicating factor. You're totally right. And the forecast products that we have don't go to that granular level right now of really the best way to handle that would be having more fine-tuned models that are appropriate at the regional and local scale to take into those kinds of variables into account. And we aren't operationalizing that kind of stuff just yet, but yeah, I guess I'm not sure if I'm answering your question. It does play a role. It definitely plays a role. I guess how I would answer it is you might expect to see different responses among organisms in an irrigated versus an unirrigated system, especially if you're in a drought setting, like where if having not enough moisture naturally would reduce activity or impact when things would occur. Am I answering your question? Okay, sounds good.
Question over here.
Hi, my question is in regards to IPM. I run a greenhouse and I feel like this information can be invaluable to my team in how we can be preventative and utilize our IPM. But in my greenhouses where, the thermal unit is in control of us and trying to figure out their lives, like any tips or any other information that we can utilize as greenhouse growers to help be preventative in our IPM with this information?
I think that the models can still be applicable, but you'd probably need to be tracking the temperature conditions within the greenhouse and calculating the growing degree day accumulation within. And so the maps that are based on daily average temperature, air temperature outside is not going to be applicable. But it's entirely possible to make those calculations on your own, and I can share some resources, like point you to some directions. There's some really good extension bulletins. Honestly, if you just Google growing degree days and maybe growing degree days, IPM, that is the place where lots of this research has been done, and there's really good extension. There's some folks out of Ohio State that definitely is stuff that I recommend maybe the most. So happy to chat with you after.
We have some questions online.
Oh, thanks. Yeah, I'm sorry. The USA National Phenology Network was established in 2007, and we have been at this ever since. And yeah, I can go into that more, and some of that's covered in the afternoon talk. Yes, so what I talked about here today, it's kind of funky. I feel like I went out of sequence today. This is kind of one side of the work that we do with the National Phenology Network with making these predictive maps and the forecasts that are continuous across the country. The other major activity that we do, that I will get into more this afternoon, is in tracking seasonal events in plants and animals through a program called Nature's Notebook. And that is where we've got folks out, with a phone app or with paper data sheets and documenting when they see these kinds of things happening. And that we've been doing since 2009. And prior to our establishment, there were very localized efforts to do the latter, to track phenology on things, not a ton, other than there was one network run out of Montana State called the Lilac Network? I think it was just called the Lilac Network by Joe Caprio, who was an extension person who had folks out across the whole western US tracking when primarily lilacs, but also some honeysuckles and even alfalfa was undergoing spring events too. So we do have some historical data, to draw from, and again, I'll talk about that more later. But in terms of this kind of work, there really have only been regional efforts to calculate growing degree days and make predictions as to when, especially pests or invasive organisms are undergoing transitions outside of our effort in this country.
Quick question, I might have missed this. Does the clock on growing degree days start December 1st or?
It's usually January 1st, and in our maps, we use January 1st as the start date. That's a fairly standard practice, again, because it's arbitrary, but it's the middle of winter in most places in the northern hemisphere.
That's interesting because you would think when plants go dormant and insects sort of go dormant, if that's the right term, you would have, you'd have a little bit of November and December to add to that.
It gets messy out here, 100%. Yes, I work with the data in Tucson a lot, and we are messy. Yes, I don't know if you all have heard of a water year before, but rather a calendar year is where you start counting day one as January 1st, and then you go to 365 or 366 to December 31st, depending on if it's a leap year. And that works very nice and neat in most parts of the country where nothing is happening in January and February, and then you start to see the first pheno phases or events in, say, February, March, April, and then it concludes in October or November, and then it's quiet in the winter. Not here, not there. No, so we use something called a water year a lot of times, which is, I don't actually know the origins, it's a hydrological thing, but it starts on October 1st. And so you go October 1st to September 30th. It makes for a headache, especially if you're trying to compare data in some locations for a water year and others in a calendar year, but it allows you to capture that kind of scenario where yes, in my yard, oh my gosh, it's such a disaster right now. It's been such a weird year. Disaster in a good way, meaning summer stuff started late and winter stuff started early, and so it's just kind of this muddle, but none of it cooperated and followed the calendar year. It was all like starting and stopping in October and November, and so I have to break up, what I call a year for capturing those biological events is October 1st to September 30th.
Keeps us humble. Any more questions?
We have a question online here, and then please, everybody, silence your cell phones.
Great. So we have Kunya Jing on the Zoom stream asks, do you have data for insect activities in terms of phenology in NPN? And then they also ask, presumably insect activities, pest as well, are regulated by temperature. Early and warm winters can be indicative for pest outbreaks later in the year, right?
Yes. Yes to all those things. I'm not sure if they're asking about whether we have the predictive maps for various insects or if you can observe and report on activities for various insects. The answer is yes to both, but it's limited in both cases. In terms of the predictive maps that we have available, it was that list that I had showed quite a few slides ago. I'll get back to it. It's largely the stuff that's the most problematic in large parts of the country. So spongy moth, Japanese beetle, hemlock woolly adelgid, emerald ash borer, Asian longhorn beetle, spotted lanternfly, all these ones that are just like, are already decimating trees or likely to decimate trees. What has shaped and driven which species we make forecasts for largely is the community and oftentimes funding too. I don't have all the logos on there, but a lot of these were funded by various discrete events where somebody came forward and said, hey, we really need a predictive map for X. And then the other key ingredient is whether a model has been established or not. Because if we know how many, say, growing degree days it takes for spongy moth to start undergoing its various generations, then that's an easy thing for us to operationalize and turn into a map like that. But if we don't know, and in a lot of cases when we have a newly introduced pest and it's rapidly expanding, and we don't know what the exact conditions are, then it's a lot harder to get to this. It either requires going back to the beginning and doing the growth chamber experiments and trying to figure it out, or models can again be established in this other way that I sort of tried to describe here, where you go out there and you make observations and you figure out when did that thing happen and what were the conditions that preceded it, and can we say, this is what it takes for that event to occur. Now we turn it into in a predictive way. But if it's a new pest and we're not seeing it in a lot of locations, then that's hard. That's really hard to even have sufficient observations for. There is another, oh gosh, I can't remember now. There's a relative of one of these guys on here, I'm blanking now, that keeps coming in from Asia, and they keep catching it at ports in the Pacific Northwest, and so it hasn't spread into the country. Maybe some of you guys know what it is. I can't remember what it is. And we've been asked multiple times by APHIS, can you make a map of that one? And we're like, well, we don't have the data yet, so it's hard. So I forgot what the question was now about insects. Yes. For Nature's Notebook, if you're interested in observing when you see insect activity, largely the insects that we have available for observing are ones that are more charismatic. Identifying insects, you guys know, super difficult, sometimes so hard. You have to look under a dissecting microscope at mouth parts and stuff. We're not asking volunteers to do that. So we really have a pretty limited list, excuse me, of insects that you can observe, because we just want for it to be stuff that you can identify with confidence. I'll get into more of that later.
Any more questions?
Thank you, Theresa. I just wanted to say before we go on break, I know we didn't get both handouts to everybody. Everybody should have gotten at least one of each handout, and we will make the handouts available online in the future. We also put all the talks online, and you can look at last year's talks as well. It takes some time to do, but they are available, handouts and all of the video presentations, sometime over the next year. But it does eventually happen, so I apologize if you didn't get both handouts today, but you will be able to get them in the future. Anyway, thank you again, Theresa.
Thank you.